Welcome to this explainer. Today, we are pushing right past the buzzwords. We hear the term quantum computing thrown around constantly in the news, right? And it's usually wrapped up in this dense jargon and totally abstract mathematics. But I want to take a completely different approach today. We're going to look straight at the incredible physical engineering behind these machines. We're going to explore what it actually takes to build a quantum computer in the real physical world.
It's the big question, right? When you think of a classical computer, you instantly picture silicon chips, motherboards, glowing screens. But what does a quantum computer physically look like? While the quantum math, superposition, entanglement, interference, gets all the glory, the harsh, literally freezing physical reality of building these devices is actually far more fascinating. We aren't just writing code here, we are trying to physically manipulate the fundamental building blocks of the universe, and we're trying to do it without breaking them.
Okay, let's dive right into this roadmap for today. We'll start with number 1, demystifying the qubit. Then 2, physical versus logical qubits. 3, the rules of quantum. Moving into 4, the quantum hardware zoo. 5, controlling the delicate qubit. And finally 6, the cryogenic chip solution.
All right, section 1, demystifying the qubit. So fundamentally, a qubit is not some magical black box. It's really just a physical quantum mechanical system with 2 distinct energy levels. We mathematically label those as state 0 and state 1. The classic textbook example of this is the spin of an electron in a magnetic field. But what makes it absolutely special is how it holds information. Instead of a strict on or off switch like a regular bit, its state can exist anywhere on the surface of a sphere, governed by these complex amplitudes. So to build a working quantum computer, engineers literally have to find a real physical object that behaves exactly like this 2-level system.
Moving on to section 2, physical versus logical qubits.
Now, we have to very clearly separate the physical qubit from the logical qubit. A physical qubit is the actual, tangible device sitting right there in the lab. And honestly, they are incredibly fragile and kind of messy. They suffer from noise, instability, and decoherence, which basically means they quickly lose their quantum state just by interacting with the environment around them. A logical qubit, on the other hand, is this stable, perfect entity that a quantum algorithm actually expects to use. Because physical qubits are so incredibly noisy, we have to use something called quantum error correction. Think of it like a massive symphony orchestra. You might need thousands of slightly out-of-tune, messy physical qubits playing together in perfect error-corrected harmony just to act as one single perfect logical qubit.
Up next is section 3, the rules of quantum. Enter DiVincenzo's criteria. Proposed back in 1996 by physicist David P. DiVincenzo, this is basically the ultimate high-stakes survival test for any potential quantum hardware. First up, the system must be scalable with well-characterized qubits. Second, you absolutely must be able to reliably initialize them to a simple starting state, like all zeros. Third, they need long coherence times. They have to hold their quantum state long enough to actually finish a calculation. Fourth, you need a universal set of quantum gates to perform operations. And fifth, you've got to have the capability to measure the final state of specific individual qubits without completely ruining everything else. You have to check every single one of those boxes, or you just don't have a working quantum computer.
Now for section 4, the quantum hardware zoo.
Now, what's really interesting here is the sheer wild variety of ways scientists are actually building these physical qubits today. It's like a quantum hardware zoo. And right now, no single winner has taken it all. Some teams are using trapped ions, where they manipulate the internal states of individual atoms literally hovering in a vacuum. Other teams use quantum dots, which trap the spin state of single electrons inside semiconductors. There's even this wild approach using the spins inside microscopic defects in synthetic diamonds. Those are known as NV centers. But one of the most prominent contenders in the industry right now is the superconducting circuit.
Let's look a little closer at superconducting qubits. Unlike trapped ions or electrons, these aren't single atoms. They're macroscopic devices. You can actually see the circuits with a standard microscope, which is pretty crazy. They're built using carefully designed lossless capacitors, inductors, and these special components called Josephson junctions. Now, because they are basically printed circuits, they are highly scalable. We get to use the standard chip fabrication techniques that we've already spent decades perfecting. So they meet a lot of DiVincenzo's criteria perfectly. But their kryptonite is that they struggle with incredibly short coherence times. They lose their quantum information very, very quickly.
All right, section 5, controlling the delicate qubit. Let's move on and see how this all builds. Looking at the quantum computing stack, you quickly realize you can't just type a line of code and have a qubit magically flip. It doesn't work like that.
High-level quantum algorithms and programming languages have to be translated down through compilers, instruction sets, and error correction layers. Ultimately, right down at the very bottom, that classical digital code must be converted into precise analog radio frequency or microwave signals. These physical waves are what actually reach into the quantum chip and physically manipulate the state of the qubits.
And this brilliantly illustrates the control problem. Notice the sheer scale of those 4 massive racks of standard room temperature microwave electronics. This entire setup, the waveform generators, the baseband controllers, all that heavy blue cabling, that whole shebang is required to control and measure just a 50-qubit Google quantum processor sitting in the shiny dilution refrigerator on the left. Just 50 qubits. If we need thousands or even millions of physical qubits to make just one logical qubit, you can immediately see the issue. We literally cannot build a skyscraper full of microwave racks just to run one single machine.
The core of this problem actually comes down to standard engineering impedance, 50 ohms. The typical room temperature instrumentation we just looked at operates in the 4 to 8 gigahertz microwave band using standard 50 ohm coaxial cables. Now, to keep the qubit stable, the quantum chip has to sit at the very bottom of the fridge at just a few millikelvin. Guys, that is colder than deep space. But sending hundreds of microwave signals from warm room temperature racks down thick metal cables into a freezing environment, that creates a massive heat and noise problem. The cables leak heat and thermal noise straight down to the qubits, completely destroying their delicate coherence.
Which brings us to Section 6, the cryogenic chip solution.
The triumphant engineering reality that aims to solve this whole wiring nightmare is something called cryo-CMOS. The idea is incredibly bold. Instead of keeping the classical control electronics at room temperature, we design them to survive inside the freezer. By moving the digital to analog converters and signal generators down into the cryogenic temperatures, so they are sitting right next to the quantum processor, we eliminate those immense thermal gradients. The wiring becomes incredibly short, and we can even use superconducting cables that have virtually zero electrical loss and actively block heat transfer. So the crucial point is how this works in practice. Take a close look at Intel's Horse Ridge system on a chip and its testing board. We're literally leveraging 60 years of traditional silicon CMOS development to solve a modern quantum problem. It's built on advanced 22-nanometer FinFET technology, which is the exact same kind of silicon manufacturing used for your everyday laptop processor. But this specific chip is designed to operate at 4 Kelvin. Sitting there in the freezing cold, it generates the exact analog pulses needed to drive and read spin qubits without melting them. It does all this while sipping such little power that it doesn't overwhelm the refrigerator's cooling capacity. It's a real game changer.
It really leaves us with a mind-bending perspective on the future of computation. We started this explainer with the abstract math of a 2-level energy system, right? And we ended up looking at advanced 22-nanometer silicon chips that have to live inside deep freeze vacuums just to send microwaves across a few centimeters of space. So as we push to scale up, as we add thousands and eventually millions of error-corrected logical qubits, will our future supercomputers and data centers no longer be these hot, noisy server farms, but instead be entirely silent, cryogenic facilities? Will they quite literally be the absolute coldest places on Earth? Well, thank you for joining me for this explainer, and keep exploring the incredible physical reality of quantum hardware.